In the preliminaries, you learned that the standard deviation is the typical distance in absolute value between the data values and the mean of the distribution. So, for example, if you were looking at a sample of 100 living women named Catherine, then the standard deviation would tell you how far an individual's age tends to be from the mean age of 51. The standard error is a really similar concept, except instead of looking at a regular distribution, like a distribution of ages, you're looking at a null distribution, something like we would use in the 3S strategy. In other words, the standard error is another name for the standard deviation, but since we're using a special distribution here, it's a standard deviation of a statistic. So let's think about using the one proportion applet to flip a coin 10 times. Okay, so for this set of 10 flips, we're going to get 6 heads and 4 tails. Let's record the proportion. So this dot represents a set of 10 coin flips, and this is the sample proportion for that set, right? I'm going to turn off the animation and we can do more, but every dot here is not an individual coin flip. Every dot is a sample of 10 coin flips where we're measuring the sample proportion. Let's skip ahead and get up to 1,000 coin flips. So we're starting to get a really good idea of what the distribution of sample proportions looks like. Let's go ahead and go up to 10,000 just to make it even more symmetrical. Okay, so now we've got a picture like this, and even though it looks like solid lines, it's actually made of dots, and each dot here is a sample statistic, right? Specifically, each dot is a sample proportion, so I'm going to write p hat for that. And it comes from a different sample. So in other words, every dot actually represents a set of 10 coin flips. Okay, so we've got this distribution of sample proportions, and when we click on summary stats, it'll give us the mean and the standard deviation. So it's not surprising that the mean here is 0.5. After all, we were modeling this based on a coin flip, so we would expect that the average proportion is 0.5, and some are higher and some are lower. But what about the standard deviation? So this standard deviation is dealing with a distribution where every dot is a statistic. So this is actually the standard deviation of a statistic. In other words, this is a standard error. So the way we interpret the standard error is similar to the standard deviation, but it changes a little bit because each dot is a statistic. So the standard deviation is the typical distance between the data values and the mean of the distribution. So let's sort of convert that. The typical distance between the data values. So here, when we look at the individual dots, those aren't individual observational units, they're statistics. So the typical distance between a sample statistic, p hat, and the mean of the distribution. So in this case, the mean of the distribution is 0.5 because that's what we assumed when we did our simulation. In other words, that's our parameter. So it's the typical distance between a sample statistic p hat and the parameter, which is pi. We were assuming in this case that pi was equal to 0.5. So in this case, the typical distance between a sample statistic p hat and the parameter pi is 0.158. So if you think about it, the distance between the sample statistic and the parameter, that's another way of saying how accurate is your estimate, right? If you're using a sample statistic to estimate the parameter, how accurate is that? Now let's think about how this changes when we change the sample size. So instead of doing a sample size of 10, I'm going to do a sample size of 428, and you'll see why in a second. So let's start off doing them individually. So pretty close to 0.5. It came out 0.472 for this one, so proportion of heads pretty close to 0.5. A little bit high this time, maybe 0.52, something like that. So we can sort of see how this distribution is building up. And let's go ahead and add a bunch. Let's go ahead and get us to 10,000. It's going to take a little bit of time, but we can get a sense of the spread here. So earlier we had a standard error of 0.158, and the sample proportions ranged all the way from 0 up to 1. Now the standard deviation is much smaller, 0.024. And if we look at the scale here, we can see it really only goes from maybe 0.43 to 0.57, something like that. So the spread is much smaller. If we want to interpret the standard error now, we could say that the typical distance between our sample statistic, I'm just going to write p hat, and pi, our true parameter, here is only 0.024. So this is true in general. As your sample size goes up, the standard error of the statistic goes down. And one way to think about this is that your estimates are getting more precise estimates. So if you're using a sample statistic to estimate a parameter, larger sample sizes are going to give you more precise estimates.